Today we're going to discuss project scheduling. We will look at the two examples that are in your textbook. Now, first of all, what is a project? A project is a unique venture with a beginning and an end conducted by people to meet established goals within the parameters of cost, schedule, and quality. So this is definition of a project. Now, what does all this mean? It is a unique venture, so it's a one-time thing, not something that you do every day. As a student, you might also be engaged in a project, for your class. That's not something that's due every week, like a weekly homework assignment, but something you do once for the semester, most likely due at the end of the semester. Now, it's conducted by people. Often a project is done by a group of people, and there will be some specified goals, like build a bridge that won't fall down. Usually in business, there is a budget associated with the project. It should be done by a certain deadline and should meet some quality standard. Here are some examples of projects. The software development, like coming with a new software or a new version of Microsoft Office, or developing a new drug that will help people with high blood pressure, or construction or renovation of a building, or underwriting a municipal bond, or other financial instruments like that. Now, the project management has gained a lot of importance these days because projects are becoming much more important as the revenue generating activity rather than the run-of-the-mill operations. How the projects are managed could now make or break a business. We will focus in this class on management of the time, that is, scheduling the activities in a project. The project scheduling tools like Gantt chart and PERT charts are used frequently in projects. Even for people who are not project managers, it has become important for them to understand such tools. Most people have probably been exposed to a Gantt chart, a bar chart that shows the schedule of activities. So you could see that we have activities lined up here. And then we have bars, each bar indicating the start and finish of the activity. Now, but not as many people are familiar with a PERT chart, the network diagram of the activities. That is down here. Now, so this is the kind of chart we're going to focus on here. There are two techniques that use this kind of network diagram, PERT and CPM. Let's go look it up here. PERT stands for Project Evaluation and Review Technique. And a CPM stands for Critical Path Method. Both of these methods were developed in 1950s, but by separate groups. Both use critical path analysis to determine the project completion time and in scheduling the activities. But the difference is that PERT is used when activity times are uncertain, and it gives a probability that the project will be completed by a certain time. Now, the CPM is used when activity times are certain, it offers the option of crashing, that is, reducing activity times by adding more resources. But today, the features of both approaches are included in any kind of project management software, so there's really no need to distinguish between the two approaches. Now let's take a look at the first example in the textbook chapter, Western Hills Shopping Center. This is a kind of construction project. So here we have a shopping center. The owner wants to modernize and expand the shopping center so that he could add more tenants. So he should be able to provide room for 8 to 10 new businesses. And we have the table here that shows the activities that make up the project. We have the descriptions of the activities, the codes or the names for the activities. And then here we have the immediate predecessors. Now for an activity, like let's say for activity C, the predecessor is A, meaning that the A needs to be completed before we could start on activity C. Now, we are also given the activity times or the durations in number of weeks in this column. Now, let's quickly go through these activities. So the first activity that needs to be completed is prepare architectural drawings. So you need to hire an architect and have him make a drawing for you. Another thing that you want to do is identify potential new tenants. Now these activities, two activities could be done right away, that they don't have any predecessors. Once A is done, once you have the drawings, you could use the drawings to do the three other activities, C, D, and E. You could develop the prospectus for tenants, that is, because you have the drawing that you could include in the prospectus. And once you have the drawing, you could also select the contractor, because you will need to show the drawing to the contractor or the potential contractor so they could make a quote. Also to prepare building permits, you need to include drawing in the permit application. Now activity F, obtain approval for building permits. To do that, you need to have the permit application. So the predecessor, of course, is E. And to perform the construction, we need to have D and F finish, that is, select the contractor, the person who's going to perform the construction, and you also need to have the approval to do the construction. So D and F are the predecessors for G. Now for H, finalize contracts with tenants. You need to have the tenants. So you need to have identified the potential new tenants and develop prospectus for the tenants. So B and C are the predecessors for activity H. The last activity, tenants move in. This could be done only if you have completed G and H, that is, construction should be completed, and you should have the finalized contracts on hand. Now, once the tenants move in, then you're done. You can relax, sit back, and just wait for the monthly rent checks to come in your mail. Now, how long will it take to complete the project? Let's try adding up the times for the activities. Let's see. So yeah, 5 plus 6 plus 4 plus 3 plus and so forth. So if I add all these times, that gives us 51 weeks. So it'll take 51 weeks to finish the entire project. So that is almost a year. Is there a way that we could do this faster? Oh, right, we could do some of the activities simultaneously. So for example, we could do A and B at the same time. Like while the architect is working on the drawing, you could be identifying the potential new tenants. What we could do is make a diagram of all the activities that will help us plan when each activity could be started and finished. This diagram is called project network or PERT network or PERT chart, so there are different names for it. Besides estimating how long the project will take, we'll also use the network to answer the following questions. When to schedule each activity, when should you start and finish each activity, and which activities are critical. That is, which activities are the bottlenecks, so that if you happen to delay this activity, that's going to delay the entire project. We want to identify those critical activities. And also, what about those that are non-critical? Those could be delayed, but how long can they be delayed before we have to worry about possible delay of the project? So project network consists of nodes and arcs. Node represents an activity, and the predecessor relationship will be represented by an arc. Now, arc is just a fancy name for arrow connecting the nodes. And there will be additional nodes besides the activities called the start node, representing the point in time when the project is started, and finish node, representing the finish point of the project. A node is going to look like this. We're going to have a box for the node, and it's going to have some information about the activity. There will be name of the activity here, and the duration of the activity, like these numbers, will be here. And then there will be information about starting times and the finish times. The ES stands for the earliest start, earliest starting time. EF would be earliest finish time. And then you have latest start and latest finish times. And we're going to, as we fill these in later, we'll explain what these things mean. So first, let's draw the network. Here's information from our table we are going to use. So we're going to start with guess what? Start node. So here is a start node. Okay, and this node represents when the project is started. Now from the start node, we're going to have arrows, that is arcs, connecting to A and B, which have no predecessors. So we're going to have here, let's put A here, okay, and B here. And we're going to have an arrow going from start to A and start to B. So this means that A and B could be started as soon as we say go, as soon as the project is started. Okay, now after A is done, we could do what? Oh, C, D, and E. So next to A, we're going to draw these three nodes, C, D, and E. Let's see, so here is C, and then D, and E. Okay, and then we have arcs going from A to each of these three activities. Now, after that, we have F. F has a predecessor E, so that means from E to F, we're going to draw an arc. So from E to F, we have an arc. Okay. Now what about G? G has two predecessors, D and F. So from D and F, we're going to have G. Okay, so we'll put G about here and have an arc D to G and arc F to G. Now what about H? H has two predecessors, B and C. Now B is over here and C is over there. Okay, this is not going to look pretty, but as long as we show the correct information. So B and C, let's say, suppose I put H right about here, and then have arc going from B to H, and then from C is going to eventually go to H. Okay. Now the last one, I, has two predecessors, G and H. So from B, G, and H, we have arc going to I. Okay, G to I and H to I. I is not a predecessor to any activity. So that means once I is done, once I is done, or I am done, once activity I is done, then we're done. So to indicate that, we're going to connect I to the finish node. So there it is. Okay, so that's the entire network. Now we're going to put the durations in here. Now we'll put the durations in the nodes. So starting with A, 5, 6, 4, 3, E gets 1, F gets 4, then we have 14, 12, and 2. Okay. Now what we could do is we're going to fill in the schedules, starting and finish times for the activities. First, we do the forward pass. Well, it tells you what to do here. Forward pass. In forward pass, we fill in the ES and EF in the boxes. ES stands for the earliest start time, and it represents the earliest time an activity can begin without violating precedence requirements. Earliest finish time is the earliest time an activity can finish without violating precedence requirements. For the initial activities, that is the ones without the predecessors, ES is equal to 0 because you could start the activity right away, 0 weeks into the project. So let's do it over here. So A gets 0 for the ES, and the ES of B is also 0. Now EF is ES plus T, that is the starting time plus the duration of the activities. So you start A at time 0, it takes 5 weeks. So when will it be done? Well, at 5 weeks into the project. So EF of A is 5. that's from 0 plus 5. And similarly, EF of B is 6. Okay. Now at C, we ask, well, let's see, when can you start on C? Well, in order to start on C, you need to be done with its predecessor. You need to be finished with A. Now, when can you be done with A? At 5 weeks into the project. So we write down 5 for the earliest time we could start C at 5 weeks. And that's assuming no transition time between the finish time of A and start time of C. And similarly, D and E will also get the 5 for the earliest start times. Now, to get the EF, we just add the duration to the ES. So 5 plus 4 is 9, 5 plus 3 is 8, and 5 plus 1 is 6. Okay, now let's go to F. F's predecessor is C, and no, sorry. F's predecessor is E, which will be done at 6 weeks. So that's when we could start F at 6 weeks. 6 plus 4 is 10 for the EF. At G, we have two predecessors, two arrows coming in, or two arcs coming in. So you gotta consider both of the predecessors. Well, D will be done at 8 weeks into the project, whereas F will be done at 10 weeks into the project. Now, remember, in order to start on G, we need to be done with both D and F. And when can you be done with both? Well, when the last of the two is done, that is, when the later one is done, which is 10 weeks into the project. So we would put down 10 there. So when we have more than one predecessor, like here, then we would choose the higher EF, the largest number of the from the predecessors. And then we add 10 plus 14, 24 for the EF. And H, again, two predecessors, two arrows coming in. So we gotta look at 9 and 6, and both will be done at, well, 9 weeks. So we put down 9 here, the larger value between the two. 9 plus 12 is 21. Now at I, again, we choose between 24 and 21, the larger value. That is 24. And then we add 2, and this was 2, then that gives us 26 for the EF of our final activity, I. So what do we have so far? What we have is, if we are smart about it and we start and finish the activity, each activity as soon as we can, then we could be done with the entire project in 26 weeks. This EF of the final activity. So far we could say the entire project will take 26 weeks. Okay, so let's put it down somewhere. Let's say big T for the entire project. The total time for the project is now 26 weeks. So we figured that out. So, and that's much better than 51 weeks. Now we're going to the backward pass. Now we're going to go from right to left and compute the bottom numbers, latest start and latest finish times for all the activities. Latest start time is the latest time that an activity can be started without delaying the entire project. And latest finish time, LF, is the latest time activity can finish without delaying the entire project. Now for the final activities, to start the backward pass, we start with the LF of the final activities, the activities that are connected to the finish node. Then LF is the project completion time for the final activities. Okay, so let's go do that. So to start the LF here for the final activity, we ask, well, when is the latest time I have to finish I by? So what's my deadline for I in order to keep this, in order to finish the entire thing in 26 weeks? Well, that must be 26 weeks into the project because I is the last activity. So we're going to put down 26. So basically, any activity that's connected to the finish node like this, the LF of such activity is the same as the project completion time. And now to get the LS here, and else is just LF minus the duration. So 26 weeks here, and we ask when do you have to start I in order not to delay the entire project. Well, we need to finish I by 26 weeks, and it takes 2 weeks to do it, so we better start by 24 weeks into the project. So 24 is the latest start time, latest time that you're allowed to start on I. Okay, now let's go to H. No, remember we're going backwards. Here, LF of H, and then we're going to look at the outgoing arcs. That is, I is a successor of H. So we're going to look at the successor, LS of the successor, to determine the LF of the activity. So here we're asking, when do you have to be done with H? Well, we want to make sure that I could be started by 24 weeks. So since H is a predecessor, I better be done with H by 24 weeks. So that's 24. So basically, you're going to look at the outgoing arc and then copy down the corresponding LS to get the LF of your activity. Okay, now here we need to just subtract 12 here from 24 to get the LS. So 24 minus 12, well, that is 20. That is 12. Okay. Now for G again, LF is going to be 24. Then minus 14 is 10. Then here for F, we have outgoing arc going over to G. Copy down 10. Put it right here. 10 minus 4 is 6. Now let's go to E. Here we copy down 6 from here. 6 goes here. Minus 1 is 5. For D, we have, 10. We copied here. Minus 3 is 7. Then here we have a 12. Copied down here. And minus 4 is 8. Okay, now here we're at A. Okay. Well, let's see. Here we have 3 outgoing arcs. So we need to select from 3 values, 8 or 7 or 5. Now let's think about this. When is the latest time that we have to finish A by in order not to delay its successors? Now C has to be started by 8, D has to be started by 7, E has to be started by 5. So this is a number we should worry about. So E has to be started by 5, so I better finish A by 5 weeks into the project. So here what we do is, if you have more than one successor, so out of the LS's of the successors like this, we would choose the smallest number to find the LF of our activity. Okay, so continuing on, 5 minus 5 is 0. And here, B has one successor, H, which has LS of 12. We copy it down here, minus 6. 12 minus 6 is 6. Okay, so that's the end of backward pass. Before we go on, I like to point out what might happen if there's more than one final activity, more than one activity that's connected to the finish node. Then how we would calculate the ES, EF, and LS, LF. Okay, so let's suppose that for the purpose of illustration, let's suppose we have one more activity, J, whose predecessors are G and H, and activity duration is 3 weeks. So what would change is here we will have, you got here GI, and then there will be another activity here, J, okay, like this, and the predecessors are G and H. So we will have arcs going from G and H to J. Okay, now we will have 3 is the duration that would go here. Okay. And then let's see. Let's say we And then from here we are going to have now arc going to finish. So now we have two activities, I and j, that are considered the final activities. Now let's pretend that we have done the forward pass, all this, and then we just did G and H, and let's do this. Let's erase some numbers. Okay. So let's say we have already done these numbers, 10 and 24, and 9 and 21. Okay, now we're going to do I and j. So let's see, for I, that doesn't change. So this is still the same, and then 26 will still be the same. Now for j, we would also have here 24. And then we would add a 3 to get 27 for the EF here. Okay, now start the backward pass. We would say, well, wait a minute. We have here, J has EF of 27 and I's EF is 26. So now how long will the entire project take? Well, J could only be done at 27 weeks. So the total time is now 27 weeks. Okay, so this is what we would use to start the backward pass. So for LF of J, we will put down 27. And also for LF of I, we would put down 27. Okay, and now I will also have the LF of 27. And 27 minus 2 is 25. Okay, and then H, let's see, H is going to be pointing to both J and I, and here we have 24 and 25. So the smaller number will be written here, and here the same thing, 24. So 24, so here we will have, that was 24 minus 14 is 10, and here 24 minus 12 is 12. And so it looks like the numbers for the bottom numbers for G and H will not change. So from there, if we were to continue with a backward pass, the other numbers are not going to change in the bottom. Okay, so here the important thing to remember is that if you have more than one final activity, and just remember to choose the total time is going to be the highest LF of the final activities. And that's the number that you would start the backward pass with. This is the number we would put in the bottom of all the final activities, like here and here, in order to start the backward pass. Here is a neater version of the project network we just created. So the next thing we're going to do is we're going to find the slacks for all the activities, and using the slacks, we're going to find the critical path in the network. So that's the definition of the slack. It's basically the delay that you're allowed to have for an activity. It's the length of time an activity can be delayed without delaying the entire project. So it's just going to be the latest start time minus the earliest start time, or latest finish minus earliest finish. It doesn't matter which difference you get, it's going to be the same. It's basically the bottom number minus the top number. Okay, so let's try getting the slack for each activity. But here we have, here we're told, okay, ES is 0 and LS is also 0. So 0 is the earliest time you could start A, and 0 is also the latest time you could start A. So there is no difference. There is no leeway. So here the slack is equal to 0. Now here, there is some delay allowed because it says, well, the earliest time you could start B is 0, and the latest time that you have to start by is 6. So the difference is a slack. That is 6 minus 0 is 6. Okay. Now what about C? Well, earliest time is 5, latest time is 8. So the difference is 3. And here the difference is 7 minus 5 is 2. And 5 minus 5, here there is no difference. And F we have 0 is a slack. Here the slack is 0, 3 here, the difference, and here the slack is 0. So those are the slacks of the activities. And the critical activities are, well, guess what? They're the ones with no slack allowed, no slack, no delay allowed. So that would mean if we were to go and circle the critical activities, A would be one of them, and then E. So we're just circling the activities with no slack, and here G and I. And notice that if you follow if you connect the critical activities by following the arcs in the network, then we get an entire path from start to finish, and that path is called, well, a critical path. So that would be going from start to A, and then to E, and then to F, and then to G, and then to I, and then we're done. So that's the critical path. Okay, so critical path here, let's write it down here, from A to E to F to G to I. So that's your critical path. So what's so special about critical path? So the special thing is that any activity that is on the critical path, we know that is a critical activity, and we can't delay those activities. So the activities that are on the critical path are the ones to focus on. They are the bottleneck activities. Also, the critical path is the longest path in the network. That is, and that length of the critical path is the same as the project duration, the total time for the project. So here, remember that the length of the project was 26 weeks. So let's see if the length of this path matches up that number. By length of the path, we mean if we were to add up the durations of the activities on that path, the sum would be the length of that path. So here we have 5, and then 1, and then F is 4, G is 14, and I is 2. So that gives me 6 plus 4 is 10, plus 14 is 24, plus 2 is, oh, that's right, 26 weeks. So length of the critical path is the same as the project time. That's not a coincidence. That is always the case. Okay, and the by path we mean, well, there could be many different paths in the network. But the critical path is going to be the longest one. So for example, let's try to identify a couple of other paths from start to finish. Let's see, how about let's say we go to A, and then C, and then H, and then I. That's a path, right? So A, C, H, I. Can you think of another path? Oh, there are many. Let's see, here's another one. B to H to I. So B to H to I. Now, so what are the length of these two paths? So let's figure that out. A is 5, C is 4, H is 12, and I is 2. That's 9 plus 12 is 21, plus 2 is 23. And BHI, that's 6, 12, 2. So 6 plus 12 plus 2, is 20. Okay, so you can kind of see, just by way of examples, the length of these paths are shorter than the length of our critical path. Well, sometimes people ask, well, since the critical path is the longest path, why choose that path? Can't we just choose a shorter path to take? Well, it doesn't quite work that way. We don't have a choice on which path to take. We do have to travel all the paths in the network, in that we have to finish all the activities in the network. So here's a kind of stupid example to illustrate this point. So say you're getting married this Saturday at 3 o'clock. Okay, so here you're going to have a wedding at 3 p.m. Okay, and you have 4 friends in your wedding party. So you're the bride and you have 4 bridesmaids in your wedding party. Let's say one's name is, I don't know, Michelle. Okay, and then we have Michelle, and we have Brittany, and let's say Ashley. And then we have, and these girls are local. These friends are local. They live close by to your wedding site. But then you have this one friend, let's call her Madison, who lives way out of state. Okay, at 4 hours driving distance. So now you want everybody to show up on time, right? So that your wedding could be started on time. And now you're not too worried about these 3 people, but you know that Madison lives much farther than others. So the distance that Madison has to travel, you would consider that a kind of critical path. Like the longest path in the network. Now you got here Michelle's path, Brittany's path, Ashley's path, and Madison's path is longer than others. So you would want to tell your friend Madison, to make sure that she starts on time. She gets up on time in the morning, start traveling, hours in advance, so that she could get there on time. So Madison is the critical activity, or you could consider the distance, like the length of the critical path. Everybody has to show up. You can't just choose one of them, but everybody has to show up. So the point of the identifying the critical path is it tells you, which path that you need to pay special attention to. Now we could see, we could answer all the questions here. What is the total time to complete the project? The total time to complete the project, we figured it out as 26 weeks. Now, when to schedule each activity, that is, what are the start and finish times for each activity? Well, we have them all here. We have them all here in the boxes. We got ES, so here we could just say, see the nodes, CES, EF, LS, and LF that we already have in our nodes. Number 3, which activities are critical and must be completed exactly as scheduled to keep the project on schedule? That we figured out, or A, E, F, G, and I. So A, E, F, G, and I were the critical activities. And how long can non-critical activities be delayed before they cause increase in the total project completion time? These were the slacks. So I would just say, see the slacks, in the network. So that's the end of this example.